Yeah, so Denny, maybe you and Liam need to talk. I'm just looking at the chat here. Yeah,
Okay,
Liam's
the
nodding his
official
head.
meeting is being recorded.
Okay, so we're now officially starting our 5 o'clock meeting. Okay, so welcome everyone. And thanks for those of you who came to office hours. We'll keep having office hours. Thank you, Hannah, for setting those up. And Darlene also. So Darlene and Hannah, you might have noticed, are our comms specialists and making sure all the communications goes out and uh, grabbing myself and Jeffrey and Troy and Juan when technical information needs to get passed out. So thank you. It's a great team, and you all are helping too by testing. So thank you very much. There's so many different options that you all have for taking pictures. We're all learning in this process. So it's fun. It's great. All right, so but today our focus is the science. And so I know a lot of folks were part of the 2017 Eclipse, and but some of you weren't, but you'll still probably want to know what were we doing and what did we do. And Juan is going to is here, and he's going to tell you kind of what he mostly and his students, with some of us supporting as much as we can, have been doing with your data, for those of you who did contribute, and what we are going, and then we'll talk a little bit at the end about kind of how this time is going to be different, and the specific science we're going to be focused on for moving forward. So Juan is a solar scientist. He is from all around the world, actually, because where he was born, you were born in Colombia, yeah?
Yeah.
And then you got your PhD in Russia?
No, I did
Your
my
undergrad.
my undergrad in Russia.
Your undergraduate degree was in Russia, and you speak some Russian, I believe?
Yes, I do.
And you speak Spanish from Colombia?
Hmm.
And then you got your PhD. I don't remember where did you get it here? I don't remember.
No, in Australia.
Australia, right. See, I knew you were around the world, where you, of course, learned English, Australian English, and then you came to the US and started working, I think, immediately at UC Berkeley.
At SSL, yeah.
Yep, where you learned American English. So Juan speaks many languages and is talented in many different arenas. And he I don't know if you ever say no. You just said maybe say maybe. So I think that's why he's been a perfect person to help with this project, because it's quite complicated. And out of all of the scientists we were working with, only he really took on how are we going to process this data, and with very limited funds. At least this time we have some real funds. So I think we'll get some actual publications this time. So with no further ado, Juan,
Sure.
thank you for all you've done, and I'm so excited for you to share with everyone your efforts.
So, hello everybody. Laura already said everything. So I will try to share my presentation. It's based on a previous presentation, but I think everything is in there. So we are going to be talking about the Eclipse Megamovie 2.24. So my brain is a little bit scattered today. And I think I need to do this, right?
Yep.
Did I do something stupid? No?
Hold on. It worked.
It worked? Okay, so it's a little bit scattered because I have been doing this. I have been preparing a rocket that is going to be launching the day of the eclipse, right? So a little bit, my brain is a little bit fuzzy. So the principle of the Megamovie, as many of you already know, is that what we want to do is to take pictures of the sun in such way that we can see the dynamical changes that happen in the solar corona in time. So if we stay only on one side, like they said in Texas, we are not going to see any kind of evolution of coronal mass ejections, plumes, jets, any kind of flow. And the reality is that because we are so close to the photosphere, the different dynamics that exist in there are related to whatever we are seeing in the other instruments like LASCO, that is the coronagraph, the one that we see at a larger distance from the surface. So there was objectives for the Megamovie. One was to observe transient phenomena, evolution in the solar corona. The second was to register the eclipse with a high cadence, so that means a good timing. And the extra bonus was to try to observe Bailey beads. So we just want to observe, not for this particular part of the Megamovie, not for the 2024, but in the original, we want to observe beads that are related to lunar topography. Since we know from many years ago, the Apollo missions and now Magellan and all of them, we know the mountains in the moon, then the Bailey beads give us a correct assessment of when the solar disk is protruding into that valley. And that will give us a very good idea what is the solar radius, which, surprise, nobody knows correctly. So everybody knows it with 1,000 megameters or one megameter of error or 2 megameters of error, but nobody knows it with great accuracy. So this is the kind of observations that we want to do. This is made by a scientist, Drunkmüller. He's a specialist in eclipses. So you can see here the different phenomenology of the corona. Of course, the moon in the center, you can see the red stuff is the chromosphere, and you can see this bubble that is popping up. That's coronal mass ejection. The big question that many people has in solar physics is that if these kind of phenomena in the lower corona is related to the bigger ones that we observe in the interplanetary medium. So is this the precursor of the giant CME? The current theory says that that's not true, that these are just mainly flows that we are going to be observing. But to have a real answer to that question, we need to see from the photosphere up to 20 solar radii, how it was the evolution of that particular dynamic structure. There are another type of structures that you're going to see here, like for example, these things that pop up. I will annotate it. These things in here, like this, these are called streamers, and these are just magnetic field lines that are open in the sun with higher solar wind velocity. In case that one of these events happen, these streamers are going to be bending, and that can give you an assessment of the material that is in there. And then I forgot how to clean it up. Just clean it up. Oh, did I clean up? Clean up. Clean all the drawings. Yeah. Okay. This is actually how we observe eclipses. In the case of the previous one, you can see a normal image. Most of us see the diamond ring in here at the top, and you can see all the chromosphere lighting up in there. The other one that we saw for the previous eclipse, these are actually data that we took from it's courtesy of one of our volunteers. You can see the 3 streamers that we're seeing in 2017. But importantly for us at that moment was mostly the observation of Regulus. Regulus played a very important role in the last eclipse. The role that it played is that it gave us an idea of what is the rotation of the field, and also how to co-rotate all the images in such a way that we can create a movie, a proper movie. By the way, if you have any question or comment, you just need to stop me and ask. This is another image.
Yeah, so
Yeah.
let me just ask, let me just be the interrupter for a minute.
Yeah.
So someone wanted to know where your rocket's being launched from. Do you know yet?
Yes, it's going to be launched from Alaska. And it's not mine. It's another person. I just have one instrument in there.
So it's to study the aurora or something?
No, this is it's Foxy. That is
Oh, so it's
a
a solar.
rocket to observe the sun in X-rays and generate images in X-rays.
We
Okay.
have a reference star we can use this time.
We have a field of the stars, but they're not as bright as Regulus. So we are kind of going to struggle a little bit with the field. So we need to be ingenious in this case. And probably use the same structures that you see here, in particular the polar regions to co-align the images.
It's one reason we have you using mounts this time too.
Right. So this is another image. I like this image. You can see how Regulus is in a different position. So these are all of you, the volunteers that make this possible. Different telescope, different mounts, different cameras, which make the challenge of this project. So how we succeed? We did when we have around 12,000 volunteers, one free app that we are not going to be supporting this time. And we got more than a terabyte of imagery that is free for everybody to download and lose their hair trying to analyze it. This is the map that you have seen many, many times and where all our volunteers were. There was a gap in Nebraska. I don't know much about Nebraska. Why there's a gap?
There was clouds and rain.
We had good weather where we were, Grand Island, Nebraska.
Just,
But I
just
wasn't part of the project then.
to the east of Grand Island, there was rain in Beatrice and Homestead. Yeah, we were just west of there too. That's why
Clear
there was
just in time.
Okay, so how the processing worked in the great steps of this thing. So we have a database in here that is all the raw data that was provided by volunteers. So that means the camera's raw data. From that, we extracted the images. We load that into a Python algorithm, and we started doing the Regulus rotation. So we created an algorithm that co-align all the images, because all of them, the lens is not perfect, and therefore the alignment with the CCD or the CMOS is not perfect. So your images of the sun are going to be a little bit squish. So we needed to fix for that. Then we needed to find all the image centers, because not all the people use mounts, and therefore the sun and the eclipse was moving along the field. So we needed to recenter all of that. And then we rotated, and that's the principal idea. With that in mind, and having all of that co-align, corrected by oblateness, and with the rotation, we applied an HDR imaging algorithm and also a Gaussian minimization algorithm to make pop up the structures, to combine them together. The naive part that I think I have, mostly myself, was that I wanted to combine all the images, because if you combine all of them and all of them are the same, then you get an image in slow motion, since you can get a lot of them. So we did that, and we created a new database, and the results of the database are images like this, which are not bad, right? These are pretty good images, but they have a lot of artifacts. So you can see Regulus in here, which is good. You can see another field star that I don't remember which one, another field star. But the other things that you can observe is this, for example, or this thing in here, and a lot of these concentric structures. All of this is because most of our volunteers did not have at the moment, or we did not push so hard for them to produce dark fields, or dark frames and flat fields. The flat field is going to erase all this. And the combination of that with the dark frame is going to create the correct normalization of the data so that we can properly analyze the different frames and kind of correlate them, integrate them together. Nevertheless, I mean,
Sorry to interrupt. We have another kind of interesting question, I think. In that image, what are the wobbly circles surrounding the eclipse?
You mean this wobbly thing?
Yeah, I think so.
Yeah, so those are my feeling is that all of that are artifacts produced by the lenses, right? Because the lens is not perfect.
I see. And this is why we talk about flats and darks.
Yes, so if we take the flats, then you're going to take away all of the imperfections of your lens, of your system, like this and dust. Maybe someone sneezed in here, so you have a droplet. So taking the flats, you can take out these kind of artifacts. So the combination with the darks that is telling you what is the current where there is no image at all will give you denormalization of this image of each frame. So when you take this picture and the one from somebody else, then you can compare them because they have the same range.
Will the temperature of the camera change that?
Yes, the temperature of the camera also affects the image and the dark field.
Which is why Tim Campbell and I, when we did our event in Wyoming for the 2017, when we did it for the Megamovie, we wrapped our telescopes with, you can get like the Mylar sheets that you get for survival blankets, but you can get some that are gold on one side and silver on the other. If you wrap them in the gold, with the gold facing out, gold reflects infrared better than silver, so it keeps the equipment more stable temperature when you're doing it.
Yeah, I bought those. They have large quantities. You buy them and you get more than you can use. So
yeah,
I've got some to give away.
Yeah.
Right.
Yeah.
So,
Okay. Thank you, Juan. Sorry to interrupt.
no problem.
I just wanted to add too that some of those artifacts also are going to come out of image processing as you try to make sure that you get the relevant features at a particular brightness. We're flattening the brightness, so you're going to be cutting out some of the pictures too.
Okay. So what are the lesson? Of course, the lack of flat field images and dark frames. That was a major issue. The other one was the not standardized bracketing time. So we had different exposures with different apertures, different diaphragms. So that makes it really challenging for us to try to combine the images and to analyze it. And I will say that that's kind of the biggest one at this moment. Also, training, we needed to do more training. So at this time, I think most of you are trained, so no need for that, right?
No, we have some brand new people.
Oh.
we'll be training folks.
Yes. So what we are expecting from, or what we did also with the Megamovie is its analysis of the data for trying to look for transients. So this is a study made by Japanese colleagues, Hanaoka et al. For the data for the same eclipse, they have, I don't remember, 3 or 4 places, four places in the US, or 3 along the path. So what they saw, if you just take a look to the images on the right, is that there are some structures that propagate upwards, like this stuff. See, it's really short in here. It's getting longer, and at the end it gets like that. So that's a jet. So these are the kind of structures that people were looking from a previous eclipse, because that eclipse was during solar minimum. 2024 is going to be on the solar maximum, so we are going to be seeing far more activity like CMEs and major flows. We decided to try to take a look for the same, using the same technique as they used. So what we got was something like this. So this is the HDR image that we have. You see this cut in here. This line. That line is because all the frames were, the centers were in different positions. So when you align them, some of them are near the edge of the CMOS of the sensor. You can see that again in here. This is a job made by Grace Kellman and mostly also by Laura. So the idea was to take the difference between these HDR images and try to see these plumes. As soon as you do that, then you can start seeing that the data is, the quality of the data is challenge. It's really a challenge.
Somebody wanted to know what time scale are the transients? So like that jet, I forget the time it took some of those jets to leave.
I think it's a minute.
Mhm.
It's several minutes.
Yeah, within the frame of view, takes
Yeah.
a couple of minutes.
Yeah, so you have, this is at 26, 34, 18. So it takes half an hour, more or less. That's
Thanks.
kind of the time scale. You have another ones that are faster, like this one. Between these two frames is faster. In case of a CME, it will take hours.
And I think that frame, like when you're saying 30 minutes, that's going about what, how many degrees across the sky? So, or is that like 2 degrees or so?
This should be about, yeah, 2 degrees, more or less, 2-3 degrees from the surface to that. Yeah. So it's the inner corona. That's what it is. But to do, so you can see the value of all this, of this project in here, because to do this image, this project, just to do this stuff, you need 3 places in the US that are going to see it at different times. Then you need to have your cameras at different longitudes and latitudes. If you don't do it, you cannot see it. So this is kind of the basic kind of idea of why this is so important. So here we have more examples. This is the Hanaoka map, or where they observe the flows. They observe polar flows, nothing in the streamers. They were polar. And this is the image that Grace made. So you can see we are not there yet with this data. And yeah, so this is what is new. We are all being prepared to have more or less identical equipment. We are going to be trained to use instrumentation and have our dark frames and flat fields. But more important, we are analyzing all this to have the correct Python routines in order to do science. And I think that's my last one with the faces of the people that made this possible. Questions?
So someone asked a question that you keep saying to me, is the solar maximum going to interfere with what we're looking to achieve with respect to the project? And I said yes, because that's what you're always saying. But maybe you could say a little more about that and why we're still gonna do good science.
I mean, so to interfere with what?
Well, just like if you have solar max, then you have all these magnetic fields. How are we going to see jets?
Yeah. Oh, well. Okay, that's a very good question.
Do you
So,
want to pull up some solar, yeah, some coronal images from NASA or something? Or
It might actually give more data.
yeah, so
It'd be helpful.
so if we see during the eclipse there is a major flare, CME, we are going to see it in these regions. This is north. Boy, my writing is bad today. Too much electronics. So this is the equatorial plane of the sun. So most of the stuff that we are going to be seeing for a CME or a flare are in these cones. Right? Jets
can you
usually
draw a line between those cones so that,
another color.
I don't
let's
know, just so that, because there are multiple, there's cones around north and south too. That's all I'm saying. So I'll just paraphrase what you just said, which is the coronal mass ejections, which are these large ejections off of the sun. We're looking at tiny features. The big features will come, yeah, there we go, where the red is.
to be seen like this or like that within these cones. But jets are usually seen is in the polar regions, like here. So I don't think the activity of the sun is going to interfere a lot, but it's going to be annoying because we all want to watch also a CME, right?
Yeah, we'd like all of it. The other thing I mean, the CMEs, generally, we don't see how they evolve in this region as well, kind of from 1.5 solar radii out to 2.5 solar radii. So there will be more information about kind of how that evolution of a CME, which we had a little bit of in 2017. You can see the CME actually on the left on this picture. This is a CME erupting on the left. And
You mean this part?
yep. Yep. And so if you go to Soho, you can actually see it. Yeah, and there's another picture of it. You can see it. It goes all the way out into the solar wind with the Soho, with the NASA images.
Yeah, so those are evolved relatively slow. So that's the more data you get, then you can see more the dynamics of it. But it takes a while.
So there's some questions about with a full frame camera sensor, what is the lens focal length you're looking for?
That's a good question for you.
I know, and I think Jeffrey can answer that probably the best of all of us.
300 to 600, with 500 being the ideal. The 500 millimeter gets you within the it's like 2.5 degree field of view. And that's vertical field.
It also depends on the whether you're using a full frame camera.
Right, correct. And I think the question was full frame.
Yeah, that was full frame. And then for an APS-C sensor.
APS-C, there's several different ones, but I think that's
300, right?
it's really kind of 275, but 300, if your lens can do 300, that's fine too. The diagonal field of view is 5.4 degrees, and the vertical is 3.0 degrees. Roughly 3.0.
Thank you, Jeffrey. I think the other thing just to add to the jets is that paper that Juan was referencing, those scientists found that that there were way more jets than NASA sees kind of at the outer, so NASA picks up information on the outer edge of the corona. I don't know, do you want to show some of the C2, C3 data
I can
or
look for.
movies? Maybe you could show some of those to kind of give people an idea of what NASA sees on a regular basis and how we're trying to kind of fill in the space that it doesn't record very often. And the jets, so what this paper found is that there are many jets they saw that they didn't see in the NASA data as the jets went out. So the question was, one is, are those real jets? And the second question is, if they are real jets, then where did they go? So we're hoping to kind of, try to validate seeing the jets, and then also try to figure out where they're going.
Okay, 1 second. I will try to.
I know we're trying. I see some of the questions in the comments, so I know. Thank you for your patience. Well, as we translate between the science units and a photographer's way of thinking about things.
There was one there from is it Jackie Talbot? He was asking about how long before C2 you can. They recommend without damaging your equipment, it's probably about 15 to 20 seconds before C2 happens is when you can take your filters off and do very short exposures. Anything before that, maybe up to 30 seconds, but I'd be pushing it at 30 seconds because you'll end up your lens will end up focusing the light of the sun and will end up burning a hole in your sensor. So I'd say 15, 20 seconds is what I did, what I and others did during the 2017 eclipse, and our equipment came out undamaged. So I wouldn't go much longer than that.
There you go. That's
Thanks, Lena.
Yeah, Fred Espinac has specific numbers on it. I'll look it up and post it in chat.
Awesome. Thank you.
there you go. That's a LASCO C2.
There's an application called Eclipse Orchestrator, and it times everything for your cameras, but it also gives you like audible alarms for when to take off your filters. I used it last time. It worked out really well.
Nice. Okay, so I wanted to show, so Juan, pull that up one more time,
Sure.
please. Thank you.
No worries.
I know some of you have seen this, but some have not. So why don't you talk a little bit about what they're seeing, right? So we've got a satellite out in space above the atmosphere, and it basically has an arm, and the arm holds a disc out in front of the bright sun. The white circle that you see in this image is essentially where the bright photosphere is. So that's what we think of as the sun. Then you can see how there's between that white circle and where you can see some things out, the streamers, or no, they're not streamers, but you see some bright things. That's still the occulting disk, and that is a place where we can get data where NASA out in space can't currently.
Yeah.
Yeah, what else do you want to say about these corona?
So when you, so this is part of the SOHO instrument, the SOHO spacecraft that is, and I think LASCO is the only instrument that is actually turned on. It's already decommissioned, but when we are observing things during an eclipse, we can see not only this part that nobody can see, different color. This part that nobody can see, we can see it further out, like more than this field of view, right? The other thing is that because of the way that LASCO works, the dynamic range is poor. So by using techniques like HDR and all that, we can achieve a better resolution than any of these images. So you can see here this structure should come like this. The same as this is from that eclipse, I think. And yes, as Laura said, this is the photosphere, that white circle. You can, utility of the eclipse is mostly to observe in this region.
Do we have other science questions for Juan? We'll get back to some of these other questions in a moment. There's some great tips in the chat. There was a question, just to confirm, CMEs go between plus or minus 45 degrees latitude of the sun, question mark, and jets from 45 to 90 degrees.
But that's in the inner corona. If you go really far out, like about 20 our sun, 20 radius, solar radius, then they can expand even more. If the CME is in the direction of Earth, then you are going to see it as a halo CME. It means that you see a circle that is moving upwards. But in general, it's confined between those two.
Right, and so then Spencer asks, any value of anticipating a CME coming straight out towards the Earth that would be hidden by the moon?
Well, if we get one, that will be awesome.
And tell us more, why would that be awesome?
Because we are not only going to see the CME, but we are going to see is the interaction of the CME with all the different magnetic field structures in the field of view. So you're going to see how they start wiggling as it propagates.
I have a question, Juan. If we do manage to get any stars as background stars during our imaging, are you going to leverage any of that to try and do any gravitational lensing measurements?
Sure, we can try. For that, we need very good pointing knowledge.
I didn't think we were supposed to have any bright stars in the field of view on this eclipse.
There isn't, but there really isn't. But if we do but some of the exposures might be long enough to pick up some of the background stars.
Yeah, the 1 second ones should, I mean, if you, with some image processing, you should be able to see the stars.
Yeah.
Hannah?
Yeah, I had what is the best case scenario? What are we hoping to do? I know that we're hoping to identify these jets, but maybe we could talk a little bit more about the significance of the potential for the data that we're receiving. Like, what questions are we answering?
What question? One of the questions that we have is the nature of jets. We do not know why they are produced in general. So we know that there is some kind of magnetic field disturbance, like reconnection, that prompts these jets to move upwards. I mean, to launch this material upwards. But how is the mechanism in which the energy is being transferred to move that material, to get the kinetic energy to move it, is not well understood. To do it, then you need to observe a lot of them. Then there is another reason for it, and is the wavelength at which we will be observing, and the nature of the light that we observe. If you take data from AIA, that's one of the cameras one of the instruments in the SDO, in the Solar Dynamics Observatory, they take data in extreme ultraviolet. So they are seeing things that are hot. When what we are going to be observing is material that is scattered, is scattering light. This is Thomson is scattering light from the surface. So what we are seeing actually are density packets. You're seeing a pocket of density that is propagating upwards, not something that is hot, because as soon as it cools down, you're not going to see that in that particular wavelength. So this is going to give us the true nature, if you want it, of that jet.
So modified DSLRs that do not have the bearing layer over the chip, which are now sensitive to IR and UV. That would give you additional data beyond just normal visual spectrum on the camera, right?
Yes.
Which will help in the research. Okay.
I actually have data images still from that, and I used a modified T3i. I had two. One was a full mod, the other one was a partial mod. I just got bad images. There was just so much blowout everywhere. It didn't matter my exposures. None of those images were any good for me.
And my T3i is modified, so and it was part of the 2017, and my images came out great. This is my image, by the way, from 2017 in the background. So that's my HDR render. And I was lucky, I got Earthshine. I did a 2-second exposure and I managed to get Earthshine in there. But but it is a modified camera, and I had to tweak it because every image looks kind of reddish because it's a fully modified camera, and the IR affects it and makes everything a pinkish red color.
Were you using a refractor or a reflector?
Yes, on an Explorer Scientific 102 refractor, 102 Apple.
Okay, you had glass. I was using a 8-inch, no, 6-inch RC. So yeah, that could have been it as well.
Yeah, it's a great picture there, and I'm glad we're doing some debugging for this next one. So, and then I see here, Gary asks, at what distance from the photosphere does the temperature of the corona start decreasing?
The temperature of the chromosphere?
Of the corona, like when does it start decreasing? Do we know? Does it stay or plateau? Does it decrease? And
So it increases up to 1 million degrees and they start decreasing as it extends in the solar wind, right?
and what is that distance from the sun?
So I will, if you take a textbook, it will give you a distance. My feeling is that there's not such a distance because it depends on of what exactly you are hitting, because that has a different height, a different altitude. So if you're looking into a flare that is pretty hot, it's going to be 1 million of degrees. The flares is going to be at 10 to the 8 centimeters. So.
And it's diffused as it moves away. The energy diffuses, so the energy is there. It's just spread out over a larger area, and that's isn't that what part of Parker Solar Probe is measuring anyway, isn't it? It's figuring out why it heats up then cools down again because it's not as hot. It's hotter off the sun's surface than it is on the surface.
Yeah, so Parker Solar Probe is measuring the solar wind. So by measuring how the solar wind, the temperature change with distance, that should correspond to a certain model on how the corona is being heat up. So the question is not the particular temperature or higher temperature the corona can have, but why the corona as a whole has 1 million of degrees temperature, right? So people don't know. It is because you have wave interactions in the corona, or you have a whole bunch of small flares coming in the lower corona. It seems like Parker Solar Probe is hinting more into the idea that you have a wave particle and wave interaction. There are magnetic waves that propagate in the solar wind that are called alpha waves. When they return to the sun, they interact with the particles and give that energy back, heating the corona. The idea from Eugene Parker, that is actually the name in Parker Solar Probe, is that you have nanoflares heating the corona. So it depends who you want to believe in this case. I mean, none of them have an answer yet.
Someone says degrees Kelvin, I assume, not Fahrenheit. Yes.
Laura, is it safe to say that starting January, we're going to start 2024 off with really organizing and fine tuning the details with all of the folks getting a scientific photos for us? We're going to have a January 29th Zoom meeting specifically for the stars. and we'll start making all of the specs and documentation live, and people can start grouping themselves by region and start organizing and chatting with each other. Of course, you can start now on Discord, but we will officially begin in January.
Okay. So yeah, answer the comment. Yes, it is in Kelvin. I am not from the US, therefore I am imperial units. I cannot use them. I don't understand them very well.
I
So-
struggle with them. I'm not from the US either, so
I do understand that they exist. I know that there is a way to change from one to the other, but I just don't. How I should say it? I mean, imperial units. Yeah, I don't know. Impaired.
So I see, right, to add to, so I know there's several threads in this in our project in this Zoom. So I know, so yes, Dar, just to add to Dar's, we will starting in 2024, we'll really kind of roll out. Today, Juan, we just I didn't get a chance to tell Juan, but Jeffrey and I kind of sent out our first draft on this gold standard that we're feeling pretty good about, but with the caveat that we'll be checking with more Eclipse photographers and make sure that this makes sense for jets. So that we'll be posting that. But in terms of like practice and instructions, Jeffrey's been kind of sharing those out for people to test. But we will have all of that out in January, and then we can, the nice thing, what we realized this time also, last time we had people just testing on the moon, but we realized this time we really want you to get, if you can, get a solar filter and test using the sun, with the caveat that the brackets are not going to be the same, because with the solar filter, unless you get a really dense solar filter, it's still going to be too bright compared with the moon, but at least you can practice, running some brackets, making sure you're pointing north, now the trick though also is that we gave you mount heads for those of you who are getting DSLR mounts from us. The mount heads are for where you're going to be, not where you are. So your tracking is not going to work quite right, but you can practice changing the code maybe. I don't even remember what we decided on changing code, but in any case, just know that as you're practicing, things aren't going to be quite right. You're going to have to, that's what's so hard about eclipses.
And just put one of the tripod legs on a brick.
Say that again, Spencer?
Just put one of the tripod legs on a brick to tilt the whole mount over.
yeah, just adjust the head.
Right.
Just adjust the head is all you'd have to do. If you've got a pivot head,
Exactly. I know you all have answers for every problem that comes along. It's so great.
I just bought some of those bubble levels that have one going one way and one going the other way, so that you know your level in both dimensions.
Right.
Here's a good tip. This is what I'm going to be doing anyway as well. You can get those digital readouts, tilt meters that you can get in a hardware store, like for carpenters use them and so on.
Oh, your phone.
Your cell phone can do it as well to a point, but sometimes the metal around the cell phone can interfere with it sometimes. But a tilt meter, and actually, wherever you are, once you have your scope lined up north, you can use a tilt meter to get it to the same angle as you would be if you were in Texas or wherever you are, to get the angle the same. So you can actually, or you can actually adjust it to suit wherever you're located. So it's easy enough, and they're not expensive. Yeah, they're $20.
I just have an app on my phone called Clinometer, I think is the name, and it does that.
Yeah. Some phones do have them, and some apps have them. But if you want to get a piece of hardware so that it's in your phone, cost $20, and it'll give you the exact tilt, so you make sure you're at the right line of latitude.
Yeah, I think this might be a good time to ask. Could I have a show of hands? So get ready to use your raise hand function in the Zoom. I know we have a lot of our stars here. If you have a smartphone capable of pointing north via an app or anything like that, can you just raise your hand if you can figure it out? So we're raising our hand if we have, oh, that works too. Raise your real hand, even better. we're raising our hand if we have a smartphone capable of pointing us north.
Although you have to say pointing us geographically north,
Geographic
True
north.
north.
True.
not magnetic north.
Yeah, true
Okay.
north. Yeah.
Okay. Thank you, Dirk. I see you. Good to see you here. Awesome. Okay, this looks good. Awesome. All right, getting some estimates. Wonderful. Thank you so much, everybody. I really appreciate it. Okay, now back to our regularly scheduled what we were talking about.
Right. So you need a smartphone that's pointing directly to Polaris. The compass uses magnetism, so it's a
Well,
different.
you can adjust if, as long as you know how to calculate the deviation for where you are, you can obviously offset that, right? So if it'll point magnetic north, and then if you know the deviation where you are, the magnetic deviation, you can actually move your scope, your mount to offset for that.
Right.
And we'll sort that out. We're mostly concerned with being able to give you a standardized, same for everybody instructions, as simple as we can possibly make it. So that's the goal ultimately.
My iPhone will
I
do
never do anything easy.
magnetic or true north. So I think there's a setting on iPhones for either direct
There is. Yeah.
north
Yeah,
or
I believe so.
magnetic. Yeah.
But yes,
I
it is
set
something
mine
we'll
for-
want to test, and maybe we can make some instructions
That's
for that. Yeah.
So
A small
one of
comment.
the things when you were talking about flats and darks and image calibration that you didn't bring up in 2016, Fred Espinette came and did a whole talk on the Eclipse. I took him to lunch and got to sit next to him and pumped him for information. And he mentioned something I've heard from nobody else, which is if you are going to use a teleconverter on your lens, so you don't have a lens of the right focal length, so you're going to pop a teleconverter, a 2x or 1.4x on to try and fix that. A lot of those generate internal reflections, and that will skew the data. So he suggests find a night with just a little bit of a crescent moon and go out and shoot the crescent moon, but don't center it, put it way off to one side of the frame and shoot it at least 6 stops of overexposure. And if your lens is going to create reflections, you should see a reflection of the moon on the other side of the image.
That brings up another point. The teleextenders change your effective f-stop too.
They do.
So you'd have to compensate for that to get the standardized f-stop.
Although if everybody shoots flats, that should be able to be calibrated out.
Yeah. Yeah, and we will go over that next month. I was at the American Geophysical Union conference along with Juan last week, and we talked to many people who have some very specific instructions on the flats and darks, and I have some apps and such. So, oh yes, look, there's Polaris. I see, Spencer.
I do
Very
have
nice.
a question about it's a technical question, but are we sending in all of the data, the calibration data, as well as the lights, or are we going to run some program that you give us to calibrate and then only send you calibrated data?
No. Yeah, Juan.
I would rather prefer the raw data with the calibration files and also your location information.
Okay.
So for example, because we need to know the height at which the sun was so that we can calibrate for extinction.
Right, okay.
And one thing about the compass with the phones, if your tripod has a ton of metal in it, it will not work. Remember that.
Yeah.
I
There was
did
some
it
discussion
twice.
on Discord about the using a cell phone for polar alignment, daytime polar alignment. And I was fooling around with Sky Safari and zoomed in. I got down to I think it was 2 seconds of precision. Of course, it's really hard when you're zoomed in that much, but if the cell phone is aligned properly with the tripod, then or with the mount, that should give you a pretty good degree of accuracy for getting your polar alignment.
Now, the very best thing is to set up the night before, assuming it's a clear night, and align it on the stars. That's the very best thing you can do. If you can't, the other option, if you can't leave your equipment out overnight, the other option, and this is what I did for not the eclipse, but I did it for the transit of Venus in 2012, is I couldn't leave my equipment out. So I went to a golf shop and bought a bunch of those orange golf tees. And I basically, after everything was aligned, I put little golf tees stuck into the grass precisely where the telescope needed to be. And I did not change the, the height adjustment on any of the legs or any of that, so that when I brought it out and set it up, it would be precisely the way it was when I aligned the night before.
Yeah, well, for 2024, Tim and I are a little spoiled because I've been working with the city of Gatesville in Texas, and they are falling over us. They're so happy to have us there because both Tim and I are solar system ambassadors. So and I'm going to be doing talks in down in the town and so on about the eclipse. But so we have a place to set up the night before and have a permanent setup and leave it there overnight is what we're going to be doing. So and the same happened in Casper, Wyoming. We had an area that we set up overnight. So and we were really lucky because we worked with the cities to get it done. So if you need somewhere to set up previously or the night before, if you can't, the polar line, talk with the city or the town that you're going to. They may have somewhere that you can set up and they'll work with you. Because it'll draw crowds to you to talk about what's going on about the eclipse, because you could become ambassadors about that. And secondly, it'll give you the ability to do alignment the night before and leave it out, just cover it, but leave it out overnight.
Liam, maybe we can send you some extra eclipse glasses and things like that to hand out.
Oh, I've in 2017 I gave out about 10,000 pairs of eclipse glasses. I did no, I'm not, that's my count. It's 10,000. How many I gave out in 2017? It was, and I can see the same happening this time around.
Totally. Okay, we are approaching time, so I think just any last comments. I love hearing the tips and tricks. I would love to see. I will maybe make a call for them on the Discord. So maybe think about what your tips and tricks are that you want to share. And then in the coming weeks, I'll see if I can do a big old ping and ask for them more formally. And yeah, maybe we can work out a way for you guys to request some eclipse glasses. We have some, we don't have a ton, but we can certainly do our best to get you as many as possible.
Okay, I want to make a verbal save the date for January 29th for stars only technical training meeting. Of course, we'll send out the email. I will check for Pacific Standard Time versus Pacific Daylight Time. I had that mistaken several emails. I'm so sorry. But it would be the same bat time, same bat channel. It would be a Monday evening, 5 p.m. Pacific, 6, 7, 8, going eastward, January 29th, stars only. If you have received a stars invite email, then you know that you're a star. And our definition of a star is someone who is either receiving our 3D printed camera mount and is agreeing to all of the technical instructions to get the scientific data, or you have your own mount and you are agreeing to be one of our volunteers to get us the scientific photos. So this is our highest level of volunteer participation, which is why we call you the stars. We're about to start our own listserv just for stars, which will probably go out tomorrow-ish. We'll see this week. And that is to differentiate you guys from just, other volunteers using Skywatcher or just general, enthusiasts and interested folks. Okay, so January 29th, put that on your calendar. And the email will come out shortly with the Zoom link. Oh, and I should just say, also, as soon as I get these Zoom recordings downloaded and uploaded onto YouTube, I will send that out via the various email listservs as well. So it will be a separate Zoom just for the 30-minute office hours beforehand, and a separate Zoom link just for this 1-hour official science meeting. So take a look at that and make sure it should come out later this week.
Yeah, let me just thank Juan again for coming and chatting with us about the science, and thanking all of you for answering each other's questions and helping us succeed in our science goals. Really appreciate it.
I had one question.
Yeah, Kyle.
Sure. I solar physics isn't exactly my area of expertise, although I'm familiar with certain um methods analysis, in my own. I'm just wondering if there are any papers or relevant literature that one could use a review to look at various techniques and methods that are being used in solar physics to analyze the type of data that you guys are going to be collecting. I'm more interested, or not interested, but is more focused on the data analysis side of things. I know we're still in the data collection, trying to get those logistics sorted. But just thinking ahead in terms of we get to the analysis portion, want to be well read and understand how to properly use the data to try to get the best science that we can out of it.
Yeah, that's a great point. We can post them on our website, the ones that are open source. We used many papers. Juan used a paper to do the data analysis for 2017, and then there are two really nice papers from analyzing the 2017 Eclipse data from Jay Pasakoff, who passed away, fortunately, recently, and then Shadia Habal also wrote some really nice Eclipse papers that I have referenced recently. And I think we can get those to you, and you'll kind of see some of the ways that these scientists who go all around the world and take photographs during eclipses, some of the ways they analyze the data. But yeah, go ahead, Juan. Yeah.
I was at the Drunkmüller, the guy that I was talking about with the image. He explains how he does the imaging. But I also caution that this has a lot of black magic.
I mean, in what way? Like wavelet analysis, Fourier transforms? Like, I don't know. I can.
I wish I could tell you. I wish I could tell you an answer, but that's it's kind of the black magic of these scientists, and they show you the path, but they don't give you, for example, the weights.
I see. Okay.
Yeah, it's all about the weighting, and there's so many parameters that you're weighting. That's why we were hoping that some of the machine learning can kind of find the optimal weights, because that's the kind of magic of it. If you're thinking of just like images and you have you do a gamma transform, right? Like what gamma are you going to use? Or if you think about like when you increase the brightness of an image, what number are you going to do that? Or you crop the image. How are you going to crop it? Or you subtract your background? How much are you going to subtract? So there are all those kind of decisions that you make in these analyses, and you try to do it objectively, but it is ultimately to try to flatten the image and get as much data out of it as possible. And so each image, so there's just all of those parameters. There's so many parameters, right, that you change. And you'll see when we release the Python code, you'll see.
Sure. Great. Sounds good. I kind of understand a little bit what you mean, because like I'm involved a lot in neuroimaging work, so I kind of maybe get what you're trying to get at. A lot of the pre-processing stuff can be a lot. I at least from if anything, if there's any overlap, I can kind of sympathize or understand where you're coming from here. Great. Thank you so much.
Yeah. No, I'm sure you do all sorts of interesting things with that kind of data. Yep.
So I want to say one last thing. I put a never expiring Discord invite link in the chat because I know sometimes they expire in 7 days and you didn't see it in your email. So never expiring Discord link. If you have not joined us on Discord, it is hopping. There are a bajillion channels and groups and ways to discuss and talk about. Hannah's on there all the time. Jeffrey as well, and Laura answering questions. It's a great place to get specific conversations and discussion happening. Ooh, almost 100 members on Discord. Go on. So scroll back a little bit and find that never expiring Discord invite and click on that. I had to learn how to use Discord just for this. So if you're new to it, we can help you, walk you through it. Yes, there are many of us that are still learning it, and yeah, it's a great way to get your feet wet.
All right. Well, thank you all for all your enthusiasm and your willingness to help science. I love it, and help our processes. Awesome. And
Thanks,
thanks to,
everybody.
yeah. Thanks, everybody.
See you
Thank
next
you.
see you next year.
See you next year.
All right, bye everyone. Be
All right, thank
safe.
you.
Bye. Thank you.